This movie deals with learning target 1, 2, and 3. It is identify isometries. We're going to develop a definition for translation, which is a movement, and develop a definition for reflection. Our essential understanding is that you can change the position of a geometric figure so that the angle measures and the distance between any 2 points of a figure stay the same. A transformation of a geometric figure is a function or a mapping that results in the change of the position, size, or shape of the figure. In a transformation, the original image is the pre-image. The resulting figure is the image. Some transformations preserve distance and angle measures. We call those rigid motion. So a transformation that preserves distance and preserves angle measures is called rigid motion. So it's basically saying, if I have a triangle, ABC, and I translate it to the right so many units, and I get A prime, B prime, C prime, everything is the same. These are two congruent triangles, so I have preserved rigid motion. Let's look at these two. Here's the pre-image, and then transformation has taken place to give us the image. So, is this an example of rigid motion? And the answer to that is, well, it's quite obviously no. If I take that pre-image and I move it to the image, there is no way that it's the same size or shape. So we say that this is not an example of rigid motion, because obviously the distance between the vertices is not preserved. Try A and B. Pause the movie to answer this question if it's an example of rigid motion, and then press play when you're finished. Let's look at this. So it appears to be a reflection, the pre-image to the image. And that is, yes, in fact, an example of rigid motion. Any kind of reflection preserves the distance, and so is an example of rigid motion. Let's look at this one. This is also yes. It would appear as though the figure is reflected and then translated up, and that, a combination of those two, also preserves distance, so that too is an example of rigid motion. A transformation maps every point of a figure onto its image and may be described with the arrow notation. Prime notation is sometimes used to identify the image points. So you can see here J, K, Q is my pre-image. And then my image is J prime, Q prime, K prime. The prime means, it's a little slash, and we say prime, but the prime means that I've done a transformation to this point, and this is the result. Here's the arrow notation. Triangle JKQ maps to triangle J prime, K prime, Q prime. Naming the images and the corresponding parts. So you can see here, we should be able to identify which one is the image and which is the pre-image by the primes. And because this has an F prime, I know that this is my image and this is my pre-image where I started. And we can see here, what are the images of angle F and angle H? Well, angle F became angle F prime. and angle H became angle H prime. So we say H prime is the image of angle H, and angle F prime is the image of angle F. It is that easy. What are the pairs of corresponding sides? Well, you can see here that EF translated and became E prime F prime. So EF and E prime F prime, EH and E prime H prime, so on and so forth. Obviously, the primes match with their pre-image. A key concept with translation, and yes, this goes in your geometry toolbox. So pause the movie and add this to your toolbox, and you're going to add that a transformation maps all points of the figure of the same distance in the same direction. And it uses a capital T for translation. It means movement left, right, up, down. Pause the movie, add it to your toolbox, and press play when you are finished. Okay, here is an example of a translation. So we took this pre-image and we mapped it to this image. How do I know that? Because of the primes. And point B went 1, 2, 3, 4 to the right, 1, 2 down. So a movement is a translation of 4 units to the right and 2 units down. Now what's interesting is we use these little things. They look like half arrows because it's acting like a vector. Our points have direction to them, and we're listing it so that this first number represents our right-left movement, and the second number represents our up-down movement. Just like any ordered pair would. So this means capital T for translation, 4 to the right, 2 down. Then what we do is we say what we were using, which was the pre-image of A, B, C, D, and that mapped to A prime, B prime, C prime, D prime. That was the result. So that's how you write it. That's called the proper notation. Let's take this example. We have a capital T here for translation, and we've got -2, -5. So the -2 tells us that we need to go left, right, and because it's negative, we go left 2. And the second number tells us our up, down, and because it's negative, we go down 5. So we take each of our points and we go left 2, down 5. So R goes left 2, down 5 to get R prime. Here's a better one. So left 2, down 5. We get R prime. Q goes left 2, down 5 to get Q prime. P goes left 2, down 5 to get P prime. And that's how we get this resulting image after a translation of left 2, down 5. Now you can do that separately with each point, or just look at your graph. Write a rule that describes this. The first thing you have to do is figure out how you're translating. So to go from point P to point P prime, we're going to the right 1, 2, 3, 4, 5, 6, 7, 8. We're going to the right 8, and we're going down 2. So we got to think through our proper notation is a capital T, which represents translation. And then I'm going to use this arrow notation here. It's like a parenthesis or a bracket. The first number represents our right-left movement. It's a +8 because I went right 8. And the second one is our up-down movement. I went down 2, so it's a -2. And I applied that transformation to PQ RS. And that mapped to P prime, Q prime, That's how you write it. So here's another way of looking at it, but you can see T8, -2. And we're going to skip this one. Opposite orientation. So that's it for translations. Now we're going to look at something that will give us opposite orientations. And that means two figures have opposite orientations if the corresponding vertices of the pre-image and the image read in opposite directions. So a BUG reads B prime, G prime, U prime. We go opposite orientations. When you reflect a figure across a line, each point of the figure maps to another point the same distance from the line, but on the other side. So the orientation of the figure reverses. Here, reflection across a line. Go ahead and pause the movie, add this to your geometry toolbox, and press play when you're finished. So yes, a reflection is when you've got a point that's reflecting about a line. Let's say we're reflecting about this line. Any point that is on that line stays on the line. Any point that is out the line, off the line, you draw perpendicular to the line and you go that same distance the other side. That's how you get your B prime. C to C prime, we start with C, we draw a perpendicular, we go that same distance to the other side to get C prime. Reflection. You can use the equation of a line of reflection in the function notation. For example, reflection of y equals x describes the reflection across the line y equals x. Reflection of the x-axis means a reflection across the x-axis. Reflection of the y-axis means a reflection across the y-axis. Reflection of x equals -2 means to take the line x equals -2 and reflect across it. Point P has coordinate 3, 4. What are the coordinates of a reflection? Capital R means reflection. Be careful with that because a lowercase r means rotation, and we want a reflection. So we've got a reflection over the line y equals 1. So let's go ahead and take our graph and graph this. Let me get a graph. We've got the point P is at 3, 4. 1, 2, 3, 1, 2, 3, 4. Point P has coordinates 3, 4. What are the coordinates after a reflection over y equals 1? So at y equals 1, I go to the y-axis at 1, and I know I've got a horizontal line, and I'm going to reflect over that line. So point P, if I think of a perpendicular, that means a vertical line, and I'm going to reflect to the other side. So it's 1, 2, 3 away, so I go 1, 2, 3 away to the other side. There's where P prime is, and that's located at, P prime is located at 1, 2, 3, -2. So 3, -2 is C. So again, a reflection has to be a perpendicular line to the line of reflection. Let's move on past that. We are going to add properties of reflections to your geometry toolbox. They preserve distance. They preserve angle measures, and reflections map each point of the pre-image to one and only one corresponding point of the image. So pause the movie, add that to your toolbox, and press play when you're finished. Note, properties you just learned means that the reflections are rigid motion, which we already learned about. So if we look at this example, we are going to see if this is an example of rigid motion. So the first thing is to graph the points this. Let me show you what that looks like. So let's get a graph. And we're going to graph the original, negative 3, 4. 1, 2, 3, 1, 2, 3, 4. 0, 1. 1, 2, 3, 4, 1, 2. Okay, now we are going to reflect, because it's a capital R, about the y-axis, and the y-axis is right here. That's our y-axis. So to reflect about the y-axis, notice B is on the line, so B prime is also the same point. Now A is on the left of the line, so it's going to travel 1, 2, 3 to the line. So it goes 1, 2, 3 in the opposite direction to get A prime. C is on the right, so it's going to travel to the left. 1, 2, 3, 4. 1, 2, 3, 4 to get C prime. So it gives us this triangle, and it's been reflected over the y-axis. Now, we can list those points. A prime is now at 1, 2, 3, 1, 2, 3, 4. B prime is still at 0, 1 because it's on the line of reflection, and C prime is now at negative 4, 2. So you can write out your primes, which are your image after the transformation. And that is it for the movie. So I would like you to please get started on your homework.